Hi, this is Shane Mueller, and this is a screencast of Chapter 4 of the Applied Statistical Analysis for Psychology and Human Factors in R book. You can play along at home if you go to this website. The course book is available right here. I have it open in a separate window. We're going to be looking at Chapter 4, which is about graphics. Chapter 4 starts, let's see, around page 67. All right, so also, if you scroll down to where chapter 4 is and go to the supplemental materials, you can download all of the figures created in this chapter are available here for looking at more closely. But you can download the walkthrough, and I think you need one or both of these data files. And I don't think there's any other data files. Also the AFL-CIO votes, I think you need. So I'm going to download that as well. And then I will move it in. I've got a special folder, so you should be able to have a folder with the walkthrough and these data files in it. All right, so we're going to open up that walkthrough file in R, and just for so we can see this pane a little more easily, I've moved it to the upper left, which is not the standard configuration. The walkthrough is down here. And so if you open it up, make sure that you change the working directory to the source file so it knows where the data are. And so the basic overview of this chapter is that we've already dealt with many really simple graphics. We've done histograms and we did some plotting and maybe some other plots so far. But now that we know how aggregation and sorting and things works, we can actually build some nice graphics. And so we're going to start by piecing together a bunch of types of graphics. These here we can piece together to do a lot of nice stuff. And then that's about the first third. And then after that, we cover some specific other types of graphing, built-in graphing methods, like a histogram, an image plot, a bar plot, a pie chart, a dot chart, and a box plot. So that is sort of what is being covered today. But first we're going to do this cumulative example where, using a lot of the tools that we've used already, we're going to create a function that makes a plot specific to a new data type. So you can't make this as a built-in function, but you can, using the tools of R, make a function that takes a data set and builds a nice plot of a specific set of data. For this, we're going to use a task called the pursuit rotor task, which is a task I've developed and used extensively, and it's a task for motor control. What happens is people see this on the screen, and here's a little target that moves around the circle, and it moves pretty quickly. Maybe once every 7 seconds or so, and all they have to do is follow it around. And so if you use this to measure people, sometimes people with certain neurological disorders will have tremor, and you can measure that. Or as people get older as they're young, or as they get older as they're old, performance will increase or decrease. Or I've used it as a dual task, so we can look at how this suffers as you're doing a secondary task. But basically what we have then is a time series where this software will send a bunch of rows, and every row is a sample of where the target was, what time it was, and where the mouse was, and how far off it is. So I have some of that data available, and it's in this pooled pursuit rotor file. And as soon as I can get the window back up, so I'm going to load this, and then we can just look at what that looks like. You can see that this has actually data from a bunch of different subjects. each subject has, each person has a unique code. They did this on 4 different trials. It's maybe about 1,000 samples per trial. We have some absolute time. We have elapsed time. So this is sort of like a computer timer. This is how long that trial was. And here we have you can see this is in milliseconds, so it's 15 seconds. We have the X and Y coordinate, the center of the mouse, and we have the mouse coordinate, or the center of the target with the mouse coordinate, the center of the mouse, whether they were on target. So there's a circle, and if they were within a certain distance of target, you see if they're on target. And that's the goal, to be on target. How much time there was between each trial, total time, differential. So this is computing the distance between the target and the mouse. And then there's a way to add up all the deviations so you can come up with some measure. So I've loaded that, and if we want to see how big this is, we can do dim of that, and we see it's 43,791 rows and 14 columns. We can look at this by doing head. Maybe we want to see how many participants we have. So if I do a table on just the sub-num, there we see I've got about 35 to 4,000 rows per subject, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 participants. Maybe I want to pick out just one participant, and maybe just one trial. So the goal here is to create a graphic that depicts what happened on a single trial. So and we'll do a little bit of exploring to see if we can figure out details of what went on in the task. So I'm going to do a filter that should be familiar now. I'm going to filter on the trial number is equal to 1 and the subject number is equal to 12818. Now if I do the dim of this, it's of the original, it's 43,000 rows, and the dim of the new one, it's 896 rows. So about 900 rows, which is one trial, about 15 seconds of recording. So now we have one trial. Now I know that, so the computer records it records repeatedly, but we want to know how fast that is, how regularly. Was it recording every half second? How frequently was it doing this? This would be useful to know. And is it actually regular? Sometimes the computer can be irregular, like it's 10 milliseconds and then it's 40 milliseconds and then it's 3 milliseconds. And so we want to know if it's sort of well calibrated. And so I'm just going to do a table of TDiff, which is the time differentials. And we can see here that of this trial, there was one that had 0 milliseconds between it. And this was, I saw earlier, was just the first trial where there was it's probably in how it's created. Like it doesn't know the starting sample rate on the first trial, so it puts 0. And then the rest are all 16 or 17 and sometimes 19 and sometimes 20. There didn't happen to be any 18s here, which is curious. But sometimes there's a little bit of a 1 millisecond lag before it records the time. But mostly it's between 16 and 17. And if you average these out, you probably find a mean of temp t diff. It's 16.75. And that means if I do 1 over that, well, it's actually it's 1 over 16.75 milliseconds is 0.1675 seconds, and if I do the reciprocal, it's 59.68, or about 60 cycles per second, which is what most laptops by default cycle at, 60 hertz per second. So we know that we're recording sort of yoked to the laptop or the computer's refresh rate. Well, is there another? First of all, maybe we want to look at this a little differently. We can look at what we might want to do is sort of create a set of measures we can do for any trial. And here's one way of thinking about that. I can make 3 plots in one by using this command. And maybe I'll plot the elapsed time. So there's that recording that says elapsed time. And we can see that on the trial, every consecutive one is recorded. And actually, it looks like a straight line. There's no real gaps there. There was also the delta that we just looked at the mean of. We can plot that, and actually we can see now that the ones that are 19 and we're actually at the very beginning. So maybe when it just starts out, there's a little stutter in the computer and it needs to catch up, and so that's at least on this trial is the only time when it wasn't 16 or 17. So that's nice to know. We could get rid of the first few samples and probably have better data. We could look at a histogram of these, and the because we already looked at the table, there's only 3 values. We can see those tables. Right now it's mostly 16 and 17 and 20 or something like that. And I found the mean of those before, and sometimes it's nice to put a line on this at the mean. The AB line usually does a intercept plus a slope, but if you use the V, it'll make a vertical line. Okay, so that's just one way of visualizing not the performance, but sort of the performance on the computer, how quickly it is recording. Okay, so, but that's really not usually what we're interested in the task. First thing we might want to know is how was that target moving around the screen over time? And so I'm going to use cbind. Cbind combines 2 columns, 2 vectors into sort of a matrix, and I'm going to put x and y of the target together. So it's basically pulling out 2 columns of that data matrix. I'm going to do a matplot of that, and a matplot plots each consecutive row of a matrix against, not against one another. Each column has a separate series. And let me do that again with resetting this. So we can see that here are the time steps that we already know are sort of regular. And then I plotted the x position and the y position. And this is sort of staggered sine waves, which is what happens if you're moving around like this. If you think about where the x and the y goes, here I'm mostly moving down and not moving over, and here I'm mostly moving over and not moving down and up. And that's what that cursor position looks like over time. I used type L because that made them lines. It got rid of the symbols. It doesn't use any symbols. BTY capital L makes the axis like this, just the left. It makes it like a big L. There's other box types. That's called box type. LAS equals 1 makes these things horizontal so that they don't overlap. I specify the x and y coordinate and the y lim. I think the original y lim was not quite, it probably chopped it off here, and I wanted enough room for a legend. So then I put the legend in, and the legend can be really fussy because it's easy to get it wrong. There's no automatic way with a plot and a legend to force these things to be the same. So it's pretty common to screw that up. There's other graphing libraries that will do that for you. So this is, one way of making another plot of that the whole trial. But this is actually the trial of the target. We could also do the same thing of the mouse. And I'm going to do that by copying this, but instead of targ x and targ y, I'm going to use mouse x and mouse y, mouse x, mouse y. I'm going to use the add equals true, so it overlays it, and then maybe I'll make color equal blue. Let's see what this looks like. So this is pretty interesting because you can see where they were supposed to be, and you can see where they were for each of the dimensions. Now this is over time for 2 different spatial dimensions, so it's kind of hard to look at, hard to kind of see what's going on. So there might be a better way of doing it, but this might be one way of doing this, and now I could encapsulate this in a function and plot this for every single trial and every single person. But I'm going to do something else. First of all, maybe I want to plot since it's a 2-dimensional data set, maybe I just want to plot them against each other, and I'm going to start by figuring out the middle of the screen. On the screen, the middle was, I'm not sure what, the middle was about 500 and 1,000 pixels, so 500 pixels from the top and 1,000 pixels from the left was the center, and that's sort of arbitrary, so I'm going to subtract the middle from each value. And you can see I calculated X mid is just a value, 958, and Y mid is just another value. And if I take temp targ X, which is a bunch of numbers, and I subtract X mid, it subtracts that value from all of them and makes them centered. So I'm going to do it within this function because I don't need to save that or anything. And plot it with some other arguments. So actually now what it did was it plotted them all. And in fact, I think it went around twice or 3 times. And that's that. Now you can't see, there's data overlaid on one another, but maybe that's okay here. So that's one plot. I'd like to use points to now plot where the mouse was at that time. I plotted it in gray, so you can't quite see it very darkly, but you can see, here's the start, and they went up. They were mostly inside the circle when they were chasing it. And then they had a little foible here, and they had to back up and stuff. One thing this doesn't show, though, is, when the target was here, where was the mouse? Was it ahead? Was it behind? I'd like to know that as well. So we're going to use segments, and this is really kind of a magical command. A segment command will make a line segment between an X, between one coordinate and another coordinate. So if I want to look at just the first row of temp, I could do temp X, temp 1, the first row, X minus mid, Y minus mid, then the mouse X minus mid and the mouse Y minus mid, and that will, for that one point, which would be like here, draw a line between where the mouse was and where the target was. But the way segments works is it can take a whole vector at once. So what I'm giving it here is 1,000 numbers here, 1,000 numbers here, 1,000 here, and 1,000 here. And so look what happens when I do that. It just drew 1,000 line segments, and it connected every target to positioned every mouse position where the person was. And now I can see, I think the way this is plotted, the pursuit path was like this, and when the angle's like this, they're behind, and when the angle's like this, they're ahead. So here you can see a place where they sort of went quickly to it and past it. As it was going along here, they went past it. So this is really nice because it can see where the target links to and also how far off it was. But remember that I recorded if they had the mouse on that circle. I'd like to be able to record which of these were they actually on target. So I'm going to go through and I'm going to plot these point by point. I could have done this in one command, but I've got maybe 1,000 rows here. So I'm going to use a for loop, and I'm going to go through each one, and then I'm going to use an if inside here and say, well, if that particular sample is on target, I'm going to plot that sample, overplot it in red. Otherwise, I'm going to overplot it in gray. So in contrast to those line segments where I did it in one command, all these red dots, I did it in 1,000 different commands. And now we can see, like this area here, they were on target, and they sort of stopped, and they got off target. And then they sped up, and they hit the target again, but they overshot it. And both times down here, it's like they hit it and overshot it. They zipped by it pretty quickly. So there's maybe something about how the mouse works at that area, or how the person's hands work when it's at the top of the screen, that goes too fast at that point. And here you can see they kind of stumbled. The target kept moving on, and then they caught up with it. All right, so this would be a nice way of encapsulating what went on for a single trial. And so I want to put this all in a function. And so I'm just going to basically copy all this code together and put it in a function. I'm going to call it plot trial, and I'm going to put header as an argument here so I can label it however I want. But then I'm going to use temp, which was sort of what I filtered out as my local argument. And this is nice because temp already exists, so I can test each of these out as I'm putting it together, and then load the function. So let's just load the function. What did I do? I calculated the center. I calculated mean offset by hand rather than, I calculated mean offset so I can put it as part of the header of this. So I can, maybe I can look at these people at every trial and say, well, here's a good trial, here's a bad trial by looking visually and looking at the header. Then these points and the segments we talked about, and then the red and green points, red and gray points. Now here I did this rather than in a loop of 1,000. I did it much like I did segments. So I plotted all the points, and then I used the color command and the on target signal to swap between red and gray at each of those points. Okay, so I'm going to create that function, and now that function exists, and instead of writing all of that code every time I want to plot a new participant, I can just run this function on a piece of code, and then we see the same thing happening, but now I know mean offset 17.93. Okay, so now maybe I want to do this for every subject. Like I could have done this, for every subject and just plotted all 4 trials of every subject. So how could I do that? I want to let me pick out one subject, but there were 4 trials. So how can I pick out each of 4 trials? So let me try it this way. I can go through the levels of trial. Trial, if we marked down what trial is, it has 1, 2, and 3, 4, and 4. So if I do this, what happens? I like to do this type of thing before I build something so I can check if it's going to work. In fact, nothing printed out and it should have, so that's kind of weird. So let me see what's going on. Well, levels of trial, there are no levels. What's going on with sub 1 trial? If I do a table of sub 1 trial, it's got these 4 levels. There's 900 to 930 samples per, but it's not a factor. Levels have to be, levels only appear in a factor, and that's the problem here. So if I say, well, that tells me what the levels are. So if I transform it to a factor, so levels of as factor, then I get what the levels are. They're the same as the names of the things that are in that table I made. So instead of looping through the levels of trial, if I loop through the levels the factor made from the trial, then I could get 1, 2, and 3, and 4, and that's what I really want, to be able to do this temp thing. So now let me see, maybe I want to make a plotting function that does a whole experiment of a single participant. So that's what this does. I'll pick up participant 12887, and then there are 4, in this case there are 4 trials, and I'm fine hard coding this because I designed the experiment. I know this is not a general purpose plotting function. This is specifically built for the experiment or the data set I have. I'm going to do a 2x2, which gives me room for 4 plots, and then I'm going to do that loop I just did, but instead of doing the filtering by hand, I'm going to filter by eye. I'm going to say I want to pick out for this subject all of the data for the trial equals first 1, then 2, then 3, and 4. And it turns out even though sub trial, we didn't change that to a factor, we just changed it to a factor here, it will still match on the text description. So this will pick out those rows for which trial is equal to 1, then 2, then 3, and 4. And in this case, I is a level of a factor that we have up here, and trial is just a character string or a number. It's usually smart enough to do that comparison properly. So I'm going to run these, and you see how it made 4 panels and it plotted them all. Trial 1, 2, 3, and 4. And we can see the same areas. Here's an area where someone had trouble, here's an area where they got off, and so on. And I can see that for trial 1, the mean offset was 17, then 23, then 16, then 15. So after they had this hiccup where they had some problems, they started actually getting better, and the last of the 4 trials was their best. Okay, so this will plot that out to a file. Now what happens if I want to iterate through everyone? So I want to look at here I could look at sort of the proportion that they spent on target for the 4 for each of the 4 trials. So this table kind of gives me a summary for everyone in every trial, and we do have some differences. Like here's someone who was on target 50% of the time in one trial. Here they went 70, 75, 75, 95, 94. In general, it looks like people get better over time, but there's a range of abilities. But what I want to do is create a document that I can look at and maybe go through with other researchers or other people to kind of look at everybody at once, or everybody. And what I'm going to do is have give everyone their own page. So I'm going to use this, and if you do, where was I? So if you use the PDF command here and give it a width and a height, and then make a bunch of pages, it will create a multi-page PDF document. So, if I do this without the PDF, it's gonna plot them all over here. You see I have a little message here so I know where I'm at, and it plotted them all over here, although you can't see them, and I could scroll through each one here. But if I do this within the PDF command, then we'll see. I'm trying to drag my I've got a, there we go. So within the folder, it created a PDF document that I can then look at in a PDF viewer. And this has subject, trial, mean, offset, and so on. And so now I basically have one document that has my whole data set visualized in it. It's no longer just a bunch of numbers in a spreadsheet, but I've made a function that does this, and then I used iteration, filtering, and looping to plot every one of them. And this might help me figure out what's going on. Well, why was that one person so bad? I could look, who is the, I can't find it anymore. If I look at this table again, let's look at 12931 and see what happened there. 12931. Well, here's what happened. They actually did pretty well for most of it, and then something went haywire just at one point, and they were so far off for that they maybe didn't even catch up for a long time. And maybe they, scratched their nose, or they had to turn off their phone and they got distracted or something. And so this would help me understand, what should I do about it? Is this something systematic? Is this something I should ignore? And looking at it like this will help me decide that. All right, so that is sort of completing the goal of creating a custom plotting function. And for a large data set, I can apply it to multiple components, and then I can visualize it in a whole document that I create. The exercise for this section has some customization of that plotting function. Okay, we've looked at histograms before, and that's what the next part is, to look at histograms. And so we're going to cover about 3 more specific new very commonly used plotting functions. And let's see. So I did this as a t-apply before, but now if I could get this score for, which is the average deviation for each trial and subject combination. And this just gives me the mean, and that's maybe not as useful as seeing the whole distribution of these deviation values. So there's a few different ways we could, but there's these different deviations, and maybe I want to see the distribution of these deviations. This is a score that I get for each person, and if I'm trying to do inferential statistics, I want to know if there's not differences systematic to every single sample, but systematic differences for the statistics we compute, like the average deviation. So I'm going to use that aggregate function to do some histograms. And there are not as many, let's see. Let me zoom in. There's not as many points. There's maybe 4 times 11, maybe 30 to 50 data points. I forget how many subjects we had. But here's what happens if I do just a histogram of this and look at the argument. I just said hist of that, and then I gave it an X label of mean deviation. So it has an automated way of dividing things up into bins, and it tries to do something that's useful, but oftentimes it doesn't give you the look that you really want. So this shows it's sort of skewed, right? Some people, not many people are below 15. There's a few people who, well, a big chunk gets between 10 and 15, but most people get between 15 and 20 pixels off. That's sort of the average number of pixels away from the target that people are, and then a few people in a few trials do much worse. But a couple customizations. It's nice to be able to change the color of this. This looks very bland, and it's nice to be able to change the number of bins. And so there's a number of ways you can specify breaks and bins, but the COL command specifies the color, and in 2 chapters from now we'll look at a lot of the options for color, but there's a lot of different color names you can use. And then instead of using these default breaks, I'm going to use breaks equals 20. Breaks is actually, the breaks command is a recommendation, so it won't necessarily do exactly 20, but it tries to get close to 20, roughly 20. And the breaks is supposed to specify the number of breaks between bins. So you might have n plus 1 bins, but in my experience, you get roughly the same number of bins, plus or minus 1, sometimes plus or minus 2, than you specify. If you want very specific control, instead of giving it a number, you give it the actual breaks. And if you give it the actual breaks, like I did here, you have to make sure you go outside the range of your data, or else it'll say there's data outside the range of your breaks, and I don't know what to do. So here I've given it specific bins, and I gave it my breaks, the integers 0 through 40. But the breaks, if you give it custom breaks, they don't even have to be equal size. So here I've sort of made a larger break and counted the number in each one of those. These you have to be careful because they can be very misleading, because you may interpret it as having more density than you should. And the other thing is sometimes these are frequency plots, so these are the counts, and you can also specify the density, which is sort of normalized. So I specified density by using the frequency equals f argument. So those are 4 sort of example histograms. The other nice thing about these histograms is, I'll just do breaks equals 40. Oops, x must be numeric. prag $x. If you set the histogram, the histogram function returns a data structure that can be really useful. It specifies what the midpoints of each break are, what the density, what the counts are, and what the actual breaks are. And so I could take this and build my own histogram, or I could use this to help overplot things because I know exactly where these values are. So sometimes I use histogram more as an analysis tool. If you want to do that, you can do plot equals false. So it just creates that data structure and doesn't plot it, and then you can make your own histogram based on those values. Okay, so that's a histogram, and there's a exercise to make histograms with transforms to see how that changes the shape of the distribution. The next demonstration we have is a box plot, or a box and whisker plot. This is sort of a very simple way of describing the shape of a distribution. And what it does is it plots, let's see, it plots the median and the interquartile range, and then sort of, I think, 2 standard deviations beyond the interquartile range or something like that. So it gives you sort of an intuitive understanding of the shape of the distribution. So what we're going to look at is this insect spray. And so here they're testing the effectiveness of 5 different insect sprays. They have multiple measures of each spray on some tree or some experiment, and on each spray they've counted how many insects were killed, so we can see which spray is the most effective. I'd like to see how the different sprays, sort of the range of effectiveness across sprays. So let me do that again with a full screen. If I do Boxplot and I give it the thing I want to look at, the dependent measure, then I use this tilde, and then the independent measure, which in this case is spray, it will make a box plot of count by spray. And here you can see this is the median. This black in the center is the median. This, I think, is the first and third quartile. And then it's in the documentation, but these things are like 2 standard deviations beyond, or one or 2 standard deviations beyond that, which should encompass sort of the estimate of the outer range of that distribution. So that's really simple. We'll do a lot of different examples of box plots. Here is another way to maybe make it, it's the same box plot, but now I can specify, what color do I want it, what is my X label and Y label, and things like that. There's also a way of making a notched box plot, and sometimes people like to make these layers. So I'm going to make a notched box plot, which gives sort of a better estimate of plus or minus 2 standard deviations, 2 standard errors. So you essentially, if notches don't overlap, you would expect, based on a t-test, that these things differ. So here you might look at these and say, well, these notches don't overlap. So actually D, even though E and D look very similar, you may expect D and E to differ in a t-test. This certainly differs from these 3. These 2 certainly differ from these 2, but this gives a visual indication of that, of what you might expect from a statistical test. So that's just another argument, and I used add is equal to true to add it on to this, so just overlaid it as another sort of layer on that. So that's insect sprays. There's another one called orchard sprays that's kind of similar, but this is, imagine you have an orchard in a grid, and you've got an 8x8 grid, so you've got rows and columns, and so this is sort of a classic Latin square design where you take the rows and your columns, and each row gets all the treatments. We have 8 different insect treatments on these trees, and you don't want all of treatment D in the first row. You want treatment D to be in 1 row and 1 column, 1 row of each column. So you have 8 versions of treatment D, 1 for each row and 1 for each column. And that's what this design does. And then so that we can measure the decrease, because in an orchard that has 64 trees in it, this might be an acre or a couple acres, and there might be differences in the sun, there might be differences in the soil and the water that they get, and so you want to counterbalance those across all possible locations, so that you can see if there's an effect of this. So we're going to use this to make some box plots and some other simple visual analyses. So if we want to look at each treatment was measured 8 times, and we want to see, let's see, if I look at help of orchard sprays, it'll tell me experiment was conducted to assess the potency of various constituent orchard sprays in repelling honeybees. So for some reason, they want to repel honeybees from these orchards because I guess they don't like honeybees. Or maybe they don't want to repel honeybees. Maybe these are a spray that that is supposed to repel other things, but they want to look at the side effects. So they want to see the least decrease. It sort of doesn't matter. We're just kind of looking at this data. And so now we can see there are some that decrease much more than others. There's some that don't decrease them at all. There's some and as as you move from treatment A to H, you see a greater decrease and a larger variability. I actually did this in 2 layers, and I like to do this on Boxplots a lot of times. So by default, Boxplot will plot sort of as single points what look like outliers, values that are outside 2 standard deviations sort of from the middle. And there's some statistical mathematical rule for that they use, but I oftentimes like to see the whole data set. So I plot all the points there too. So this gives me a better feel. One of the things a boxplot hides is how many observations you really have. And some of these long whiskers might come from just 1 or 2 observations. So the boxplot lets you specify multiple independent variables by which you plot them. And so using sort of this plus argument, so I can ask for treatment by row position. And in this case, it's not very helpful because I've got, first of all, I don't have any more than 1 observation in the treatment by row position condition. And then there's 64 different columns. So that's not very helpful, but sometimes this can be if you have fewer conditions. Another way to use boxplot, though, instead of saying argument by levels of another thing, is to use a data frame. So here is a data frame with 3 different, we'll look at it, 3 different columns. The sales at 3 different stores, and if I do a box plot of just that, without the tilde, without anything, it will do a box plot of every column. So that's a different way of using the same function, and sometimes you forget about one or use the other. In this case, let's see. You have to be careful of doing this, though. In this case, the 3 sales figures were relatively similar. And if I happen to have a data frame that has very different data sets, like birth date and tenure at company, and I put these here, even though there's variability within each dimension, you don't see it because it gets compressed. The birth date was in the 1900s, and the tenure is in between 0 and 40 years or something. So they just look very compressed. So you have to be careful. You'd only want to put multiple things on the same dimension if they are sort of the same values. Using a data frame allows you to put things of different dimensions on the same axis, and it sometimes doesn't make sense. Okay, so that is just some examples of the box plot. We're going to do some even more fancy, more advanced box plots in the next chapter. So we'll return to those because they can be, there's other ways you can use them. Next, we're going to look at an image plot. An image plot is sort of a completely different thing. It's sort of making a bitmap, a visual bitmap of something. So I can take each of these decreases, and notice I had row and column position, and I can do t-apply. So think about what this is doing. Before I show you, I'm applying decrease. I'm finding the mean decrease for each row and each column. Now there happens to only be 1 decrease in each row and each column. So it looks like it's finding the average decrease of each row and each column, but there's only 1 tree in each row and each column. And so what it really is doing is reorganizing the long format into a matrix, into a grid, even though there's only 1. And so sometimes if you had multiple observations for each condition, this makes sense, and you forget that you can do it even if you only have 1. even if you have 0 in some, those would turn out to be NAs, and this would still work. The image plot sort of plots this matrix up on the screen. So if I do image, and I'm going to give it the X and Y coordinates that I want to make it easy. It plots it in a weird way though. So first of all, the darkness of this is going to be related to the value in here. The rows get plotted from bottom up, or it's really weird. If you're looking at this, these are the rows. So this here is this. And we can see that the brighter it is, the larger the value. So you see this white one here corresponds to 130. This really dark one here corresponds to 7. So, but it's all, this goes from down, from top to bottom. This goes from bottom to up and right to left instead of top to bottom. So it can be confusing trying to map this onto this if you're trying to link the two. And so sometimes you have to sort of transform one or transform the other to get the figure you want. Another thing I can do now, but since I have that original data set, I can use text. Text is just like a plot or a points function, but instead of putting a point, like a symbol, it puts a piece of text. And if I use the decrease as the text, I can plot the level for each one of these. Except, and now we can see, the row position by the column position. It'll put it right at the center of each one of these, and this helps me interpret these values better. So 130, 127, the lighter it is, the higher it is, the darker it is, the lower it is. And now it's almost like we're doing a aerial view of this field, and we can see that, well, this is kind of weird because there's this area here. We don't know if it's just by chance or because there's a bad area in the field where the decrease is very minimal for everything. So maybe there was a problem in the middle of the field for some reason. So this image is really handy. This is just one color scheme. There's a lot of different color schemes. You can make custom color schemes as well. You don't have to build something with t-apply. You can make your own matrix. Image requires a matrix or maybe a table, which is kind of like a matrix, to work. So I can make a matrix out of these values, 7 by 7, and then I do image plot, and here's my grumpy face that I just drew, and you can see how the eyes are here, the nose, the mouth here, maps on to these things. And in fact, if we look at data, you can see how when I put the matrix like this, it does it by row, by column, and so this row becomes this column. And so these things map onto this down here. Let's see. I use image plots to do sort of, oftentimes to plot a bunch of variables and how they correlate with one another. And so here's a data set about irises, flowers, and there's there's 4 measures on irises: the sepal length, sepal width, petal length, and petal width. And this is a sort of a famous data set within R. It's used for a lot of demonstrations, and I can compute the correlation of these things. So across, petal length and sepal length are very highly correlated. And sepal length and petal width are highly correlated. So if a flower has long petal length, it tends to have long petal width or large petal width. I could correlate the other way though too. And so if I just display this, these are a bunch, 100 and some flowers, and we can see on these 4 measures which ones are correlated with one another. Some are very highly correlated, 100, 99%. Others are low correlated, which means they have a different pattern of relationship. So I've just calculated, 150 by 150 matrix, and I'd like to visualize it. I can do an image of that, and this helps me look at other things. So now let's think about what's going on here. The brighter this is, the higher the value, and we can see it's like there's a set of 3 different types we can see without knowing anything else about it. There's the first third are all highly correlated with one another. They're very similar with one another. Their relationships are very similar. Then you see these sort of darker areas, so they're kind of similar to these and less similar to these. We see that these 2 groups are fairly well similar to each other, because we look at this, and then we see group 1, I guess, is most dissimilar to group 3. So this would be a way of visualizing a large correlation matrix that could be helpful if you have a lot of different predictors and do classification or something. I also use it for sort of like a 2D histogram. So here is some data that are sort of related, and what if I can create a table out of this by taking, say, these values and rounding them to the nearest integer. I'm going to use ceiling as a round. So, and then making a table out of them. So txy, it's sideways from this, but it says, well, how many things had 4 on the first value and 3 on the second value when you do a ceiling argument? And that happened to be 14. So 4 in the first and 3 in here. There's a little square in here that if you count them up, there's 14 in there. So that's what this table does. If I take, let's see, if I take x, those are those raw values that I plotted. If I take ceiling of x, those are the integers, and I can treat those as bins and make a table, and I get this thing. So what if I plot that table? Now you can see it's actually shows sort of the brightness is related to the density of this. And you can see this little square here and this little square here. There's a lot more. And if I do all the alignment right, because the grids are not that easy to get right, I can plot the points on top of that. And I can see the actual points, which are the same here, but plotted with little yellow squares, and also sort of the density. So this would be a nice way of making a 2D density kind of histogram. All right, so that's image plots, and these can be useful in a lot of different ways. Next, we've got bar charts. And a bar chart is, a plot that draws like this, that draws a line from 0 to the value. And there's a way to make like a cheap bar chart using the type H of a regular plot. And usually the interesting thing about bar charts is they imply that 0 matters. They imply the distance between the bottom and the top matter. That's not always true. Like you wouldn't want to usually plot like temperature as a bar chart unless the baseline, like the average temperature in 1970, is something that you care about, and then try to look at then you'd score it at, temperature above average in 1970 or something like that. So usually it implies that not only the distance here, but also thus the ratio. So since this bar is twice as high as this bar, then that's what this sort of implies that. The other thing people like to do for bar charts is they like to plot categorical variables. People violate it all the time, but some people say, oh, you should never plot a continuous variable on a bar chart. It sort of implies different categories. And so that's a rule that you should think about. Violate it when necessary, but some people sort of treat it as a religious doctrine, and that you can only use categorical variables in a bar chart, sort of different categories. Certainly, if these indices were ordinal, that would be fine. If it's continuous, you might be better off using a dot, like a line chart, especially if your vertical axis has sort of an implication of that 0 doesn't matter. Here's some ways of doing bar charts, some arguments that we'll look at in a second. Okay, so I'm going to zoom in on this. So the first one is I just plotted these 4 values, and then down here is the names argument. It's called names. It's not going to be axis labels or something. And what you can see here is this sometimes bugs me. On the left axis, these are turned sort of to the left. And if you use the LAS argument is equal to 1, it'll make all of your numbers sort of read from, oriented horizontally. The third one I did was, first of all, just like in histogram, it returns a value. If we look at what axis is, which is what I returned, it returns actually on the plot it makes. It's not clear what the vertical numbers are, and it returns what those vertical numbers are. And so I then use text to say, I want to plot these 3 numbers here, A, B, and C, at the top of the columns, so I can, and they happen to be at 0.7, 1.9, and 3.1, and you'd never be able to figure that out just by trial and error. Well, it would take a lot of trial and error to do it, and so if you barplot returns those values for you. And finally, you can do them sideways. And this could be helpful if you have really long text descriptions like questions in a survey or something. It gives you a little more room to write. You would extend your Y margin a lot to do that, but I've done that in the past as well. Now, a bar plot will work if you use negative numbers. And whether they're positive, there's positive and negative or negative, it'll work there too. And now this might be, maybe you want to do this for some reason, sort of your axis on top, but these are actually positive values. You could get rid of the axis, fake your numbers so they're negative, get rid of the axis, and then add your own axis. The axis command adds an axis, and here I'm going to make it from 0 to negative 10, but I'm going to give it 0 to positive 10 numbers. So I've sort of faked a different axis of numbers on here rather than using the built-in one. Maybe this, the label of this is degrees below 0 for consecutive weeks of January and February. And so you could see, it's nice to show it below, but since this would say below 0, then you're not negative below 0. Those are degrees below 0. However, here's one of the problems with bar plots. Here I've plotted the values 1000 through 1010, and you can just barely see a difference. There's a slight difference here. And maybe you really care about that difference. So, this might show that you shouldn't be using a bar plot if you're doing this, because again, bar plots sort of imply that there's a 0 that matters. And if you think that the difference between 1000 and 1010 matter, probably 0 doesn't matter in that case, and you should avoid a bar plot. But you can still change the Y limits. I could set the Y limits between 1000 and 1010, but then this happens, and this is, I don't think there's any excuse for this, why this happened, but it sort of falls down the bottom side of the axis and disappears. Well, how do you fix it? This is something that you have to look up online to figure it out, and you can use the xpd is equal to f argument to get rid of that. So if you ever need to do this, this will still sort of imply that there's stuff below 1000. I chopped it off at 1000, but it doesn't. At least you have a bottom margin that you can look at. You can use bar plots with multiple series, so so you get the same numbers. I'm gonna create a data set, and this might be like answers on a questionnaire, and so you don't really have maybe you don't even have correct answers. Maybe these are opinion questionnaires, and so the average doesn't matter, and you just want to see the distribution. So here's what the data table would look like. A through E are the different options. Q1 through Q5 are the questions, and I'm going to load a library called Gplots. This is which I don't have installed here. Well, we'll have to. If you don't have Gplots, you would go over here and install it. and it should just take a second to install this. But I'm using this for a color display. It has a nice color scheme in it, so I'm using that. We're going to go over that color scheme in a future chapter. So here's a way of making a bar plot, and because of the way I did it, I plot this table. I made it horizontal. I changed the the direction of the labels and stuff, and the color I used the first five built-in colors. And so this shows me, oh, most people were saying 3 here, most people were saying maybe 2 here, most people are saying 5 here, and so on. So that could be helpful in understanding where the responses were. But here's another. Okay, I installed the Gplots, but I did not load it. So this loads special built-in libraries. And so I'm now going to plot this with a special color scheme. And so you can see sometimes kind of an ugly plot becomes really nice if you specify a color scheme you like. So these are what look like stacked bars, and they all happen to be equal because in the table the row sums are equal too. But what happens if you have uneven values? Here's an example. This code will load a table directly from here, and this is from a data set that looks at sort of residential juvenile detention by race across different states. And so this is just a little processing to make it work. But if I do a bar plot here, I've got the first 5 states by alphabetical order. How many residents are there? And you can see, well, California has a lot more. They have like 7,000. And in fact, because of that, it compresses all these other things. Well, this might be useful because you might realize that most of the detentions in these states are from California, but it also hides some of the differences here. And so I plotted another thing which equalized the columns. So this is the same data based on this normed thing. So this is the original data, and the normed version sort of divides by each state by the total in each state, and then multiplies by 100. So these are percentages. So now either one of these can be informative, but the stacked bar is especially useful here. And it's useful here because as long as it's labeled right, because it implies that now we're looking at proportions. Regardless of how many at an absolute value, we can see, oh, look, Alaska has many more Native Americans in this program. Arizona and California have many more Hispanic in the program, and so on, which you can't really see here because it's so compressed. All right. So a bar plot, if you don't want it stacked, you can use this beside is equal to true, and this will make basically a little histogram or a little series bar plot for each one. And in both cases, you always have the choice of, do you want to organize by question or answer, column or row? And I can flip that by putting it in a T command. T transposes that table. So if I look at data table versus T data table, that this row is this column. I could put the same ones in a stacked way as well. So there's a lot of different ways of organizing the same data, just depending on what you want to show. All right, let me pause for a moment. The next chapter will also be on graphics, but this will be a set of more advanced graphics. We're going to look at error bars and a few other more advanced built-in a few more advanced functions using images, using bar plots, and then there'll be a third graphics unit related to really advanced packages that do really interesting things that you can't get, sort of making alternative and beautiful graphics for using other systems. All right, thank you.